In the previous video, we looked at all the different things that go into ring opening reactions of epoxides. And in this video, I'm going to look specifically at some examples. So in our first example, we want to predict a product and draw the mechanism of the following reaction. What I'd like to do first is predict the product, and then we'll figure out what the mechanism should look like. Now, the first thing we want to ask ourselves is, which of the two types of ring openings do we have? Do we have a strong nucleophile, which has one type of mechanism and one type of regiochemistry, or is this the weak nucleophile with acidic conditions, where we have a different regiochemistry and a different mechanism? I think in this case, right, the sodium is just a spectator ion or a counter ion, right, and so our nucleophile is really this negatively charged sulfur, right? And so that's going to be a strong nucleophile. So that's going to follow the first type of ring open reactions that we learned in the last video. And so it's going to follow typical SN2 reaction properties. And so we're going to attack the less substituted center, and we're going to get inversion of configuration. Now, when I draw this product, there are two ways that I think it's easiest to show the inversion of configuration. When we first learned about drawing inversion of configuration, what we talked about is, for this chiral center, when we're going to invert the configuration, we're going to change all the wedges to dashes and all the dashes to wedges. So one way to draw this product would be the OH ends up on the more substituted carbon. That carbon wasn't attacked, so its stereochemistry should stay the same. Right, and then we can replace the oxygen with our new nucleophile. And then, because the configuration of this one should have changed, right, we've got to change the wedge in the reactant into a dash in the product. And so I think this is the correct product, right, because it's an SN2 mechanism. The nucleophile attacked the less substituted carbon, so our nucleophile ended up here. And then we've also correctly shown the inversion of configuration. Now, the way the book would have drawn this product is slightly different. And so the book would have drawn it. So this carbon is going to draw the same as we did. And then when we get the backside attack, right, and I think the way the book's drawing it is almost, they're both absolutely correct, but the way the book's going to draw it is kind of showing more specifically what's going on in this reaction, right? So this nucleophile is going to come down here, right, and then it's going to sort of, when I think about inversion of configuration, I think about sort of turning an umbrella inside out. And so when the sulfur attacks here, right, it's really going to pop the methyl, and then the hydrogen here that we're not showing is going to pop up to the other side. And so the way the book would draw it is he put the methyl there, and then our nucleophile being added there. And now we didn't just swap the wedges and the dashes, right? In this case, we're sort of turning the whole thing inside out, and so we're really drawing it in a whole new configuration. And so at first it may be confused, like, well, it's on a wedge, but we're not drawing it in the same orientation. And so to see that these two are in fact the same, if you get a model kit or kind of use your fingers, right, imagine what's going to happen to this methyl if we take the sulfur and we rotate around this single bond so that the sulfur becomes in the plane pointing up. And I think when you do that, you'll see when that happens, when this guy gets rotated to this position, that methyl is in fact going to be rotated so that it's down and on the dash. So both of these are exactly equivalent ways to draw this product. I think when I first started doing these examples, this first way made more sense to me, right? Just replace the oxygen with our new nucleophile and change whatever was on the wedge to a dash, and if there was a dash, we would change it to a wedge. And that's a perfectly okay way to do it. The more examples I've done, I think I kind of like this way better. They're both absolutely correct. Whichever one of these you draw would be perfectly fine. Just be sure that you're showing me the correct inversion of configuration. All right, so either one of these would be correct to draw for the products. Now we want to draw the mechanism. So I'm going to slide this up to give ourselves a little bit more room. All right, so for the mechanism, our starting material, the first thing that's going to happen is we're going to have the attack by the nucleophile. So I'm going to leave off the sodium. That's just a counter ion. Right, so our nucleophile is going to attack here. That bond will become a lone pair on the oxygen. That oxygen is now negative. All right, we've attached our nucleophile, and then the last step in the mechanism is going to be proton transfer. So we have the water. It's going to have its hydrogen stolen by that negative oxygen atom. And so in our mechanism, we first have an SN2 step, and then we have a proton transfer to give us the product. Okay, here's a second example. Again, the first thing we need to decide is, do we have a strong nucleophile or do we have acidic conditions? In this case, we have a Grignard reagent, so this is again going to be a strong nucleophile. And so we're going to attack the less substituted position, and we're going to get inversion of configuration. Now, this carbon is not chiral, so I don't have to worry about the inversion of configuration. So my product is just going to be and then the nucleophile that we're adding in the Grignard reaction is this R group, the ethyl group. And I don't have to worry about showing any stereochemistry here because I have two hydrogens, so this guy's not chiral. So this is going to be my product. And then the mechanism so what I really have is the negative ethyl, if you will, and then the rest of the Grignard reagent isn't really involved. And so my ethyl anion is going to attack there. Bond becomes a lone pair on the oxygen. So my intermediate add my nucleophile, and then the last step again is a proton transfer with the water. All right, and so that's my product and the mechanism for this example. All right, here's another example. And again, we want to ask ourselves, do we have a strong nucleophile or are we in acidic conditions? Right, I think this case we're in acidic conditions. So the mechanism is going to be slightly different, and we also have to be careful of the regiochemistry, which is also different. Now, under acidic conditions, if we have just, as we do in this case, primary and secondary carbons that are part of the epoxide, the regular SN2 regiochemistry is going to be followed. And so the nucleophile is going to attack the less substituted carbon. Again, we're going to get inversion of configuration, but because this carbon's not chiral, we don't have to worry about that. And so all we need to do to draw the product is just slap the chlorine on this one. Of course, being sure to keep the configuration of the other carbon the same because it is chiral. But because that was not being attacked, its configuration won't change. So my product will look like that. Now for drawing the mechanism, under acidic conditions, the mechanism is different than when we have just a strong nucleophile. Right, essentially is backwards. With a strong nucleophile, first we had the SN2, then the proton transfer. Under acidic conditions, first we have the proton transfer, And then we have the SN2 step. And that'll give us our product. Okay, one last example. Again, we want to ask ourselves, do we have a strong nucleophile or do we have acidic conditions? In this case, with a weak nucleophile. So we have acidic conditions, a weak nucleophile. And so again, we have to be careful of the regiochemistry because this is where it's going to be a little bit unusual, right? If I have a tertiary carbon that's part of the epoxide, counter to what usually happens in SN2 mechanisms, this is where my nucleophile is going to attack. And we're going to get inversion of configuration. And so when I draw my product first, right, the other carbon that wasn't attacked, its configuration stays the same, right? And now I need to invert the configuration when I add the OME here, right? And so we can either put the OME on the top and then swap the methyl and the ethyl, or I'm going to do it the way the book does, right? And I'm going to push the methyl and the ethyl up. And then we'll put our nucleophile down on the bottom. All right, and then the mechanism for this, we're going to start with a proton transfer. We're going to follow it up with an SN2 step. In this case, my proton source I'm going to draw it as hydronium ion, which is typical to what we do when we have sulfuric acid as a catalyst. So my oxygen is going to steal that hydrogen. Now my nucleophile is going to come in. And then because this oxygen is positively charged, I need to finish off with a proton transfer to pull off that proton. Because my nucleophile is methanol, it's going to be methanol that does this as opposed to water. And so we've got a three-step mechanism in the case where we have acidic conditions and a weak nucleophile.